binary search trees, and the whole point of a binary search, a self-balancing binary search tree is that, well, this. So maybe we discussed last time that the worst case in any binary search tree of insert, delete, and find could be O of n or theta of n, because the binary search tree might be highly imbalanced. And so we discussed now for a binary search tree, what is the smallest possible value of the max depth. So this was a bit wordy, but the point was we're trying to understand what are the limits of using a binary search tree. That if you had a binary search tree of the best possible shape, how long will it take to insert, delete, and find? And there's this lemma that basically says that for any binary search tree with n nodes, there exists a node with depth at least log base 2n. Right? So there's always some node at depth log base 2n, which means that no matter how you structure your tree, there is an insert or a find that's going to take log n time. So the best you can hope for is for getting log n time for all operations. That would be the best one could hope for with a binary search tree, and that is exactly what a self-balancing binary search tree achieves. It always maintains a depth of log n, theta log n, right? So it's not going to be perfectly balanced, but it's sort of, one can think of it as balanced up to a constant factor with respect to the depth. And a specific example is the AVL tree, which is the one that I will be teaching. The key to understanding all of these self-balancing trees is this operation called a rotation. So what a rotation does is it sort of, so this is it's a complicated picture, but the idea is it's an operation that moves a child to its parent's position. That's the way to think about it, right? So you have some node like y, and a rotation, so different texts consider it differently. Some call it a rotation at x, some call it at y. I prefer to think of it as y because it's like this node has to move to its parent. That's a rotation operation. So y moves to its parent. And the way it does that is that after this rotation, x becomes the child of y. Right? So y will move up, x will move down, and then these subtrees over here have to be readjusted. And the parent also has to be the parent pointers have to be readjusted. So there are a bunch of pointers that need to be readjusted with this, but it's only a constant number of pointers, and so rotation can be done in constant time. Right? So it doesn't depend on the depth, it doesn't depend on the number of nodes, it's just an absolute constant number of operations to perform this rotation. And so you have left rotations and right rotations, but again the point is in any rotation, it's some child is going to move to the parent. So we'll call it left and right depending on whether it's the left child or the right child. But again, I think that just to keep things like simple, clear, just think of it as a rotation is going to take a node and move it to its parent's position. And do it in such a way that the BSD invariant is not destroyed. Like when you move this, you have to ensure that all the values are preserved in the right way. Does this make sense? Any questions about rotations? Okay. So how does, okay, so good. Now we have that. So I'll just keep this, I'll keep the rotation picture up here, and let's talk about AVL trees. So for that, we've been talking about depth, which is also equivalent to height. So I'm just going to use the term height here. So I'll say the height, so the height of a node x, which is equivalently the height of the subtree rooted at x. So what we're saying is we have some tree here. Let's consider some node x. The height of x, or the height of the subtree rooted at x, is the distance of the furthest leaf from x in that subtree. So it is the max distance of any descendant of x from x, right? So you're looking at every descendant of x, and you measure the distance, and we'll measure distance as the number of nodes on the path. Although usually it's number of edges is probably more common, but we'll just do the number of nodes. That way the height of a leaf will be 1. Actually, let me think about it a bit. Should I do nodes or? But sorry. No. The height of the root is actually going to be large. So I'm going to look at the number of edges on the path. So what this means is if you take a leaf, the height of a leaf is always 0. Right? Because you're looking at the max distance of any descendant of that node from that node. So if you're looking at the height of the root, you're looking at all descendants of the root, which are all possible nodes, and you're looking at the furthest one. That's the height of the root. The depth is the distance from the root. I guess, the problem with trees are they're the opposite of what they are in real life, but leaves are on the ground. Yeah, it's fall. Good. Yeah. Very appropriate. Right? Well, the root is also still in the ground, so it's at some point it fails. Okay, yeah. Height and depth, sure. So, so for this node, that distance is the depth, right? It's the distance to the root. The height is how high it is. So the distance to the furthest leaf, that's the height. Does that make sense? So maybe just give an example. Let's take some tree that I already have, or let's just draw some tree here. Right? So if you look at the leaves, they have a height of 0, right? Because what is the descendant of a leaf? The only descendant of a leaf is itself. And the distance is being measured in edges, and so the height is 0. Does that make sense? So the height of all of these is 0. The height of these nodes is 1. The height of these nodes is 2. And the height of the root is 3, because if you look at the furthest leaf away, there's this path of 3 edges from this leaf to there, and therefore it's 3. The depth would be the distance from the root. I'm measuring height, distance in terms of number of edges, right? So it's 1, 2, 3. Okay, fair enough. So height 0, 1, 2. There, that was a mistake. 3, 4. Okay, good. Thank you. That's correct. That's correct, right? So everyone's checking this, or am I? Yeah, that's right. So the height of this is 2. The height of this is 3, 4. So everyone who laughed, at least, I guess they're following what's going on. So good. Okay, is that clear? Whoa. Ooh. Today's not my day. Does that make sense? That's what the height of it. Yes. Say it again. To the furthest leaf, like the height of a node is the number of edges to the furthest leaf. Right? That's the height. And when we're measuring depth, we're measuring distance to the root. So the height is, again, the height of a node x is also the height of the it's also called the height of the subtree rooted at x, because you're only looking at things that are descendants of x. Does that make sense? Yeah, so that's the definition of the height of a subtree. So why am I talking about the height? So what does it mean to be perfectly balanced? So let's just think about that. Like, why am I talking about heights? Because in a self-balancing tree, you're trying to have the tree be perfectly balanced. So can you try to describe what it means to be perfectly balanced with respect to the heights? Yes? There are only two distinct levels of heights, or rather, well, you have to be careful because, but yes, there are two distinct levels of depth, I guess, of the leaves. The leaves, the distance of leaves from the root, there are only two possible values, right? Or, yeah? You mean nodes at every level have to have the same height? That would be perfectly balanced, exactly. And technically, you can't get it to be exactly that, so it would be one of two values. Right? Because if it's not exactly like a power of 2 minus 1, then you could have some nodes that are off by 1. But essentially, yeah, that's the whole point, right? So if you look at all the nodes at this level, they should sort of have ideally the same height. Right? So if it's perfectly balanced, then if you look at all the heights, so it's 0 here, it's 1 there, and it's 2 over there. Right? So all nodes at the same level have the same height, where technically level is kind of like depth. But anyway, if you're getting confused, just think of height. Right? So if you have this notion of levels, all the nodes at a given level have the same height. That's what it means to be perfectly balanced. Now, because suppose, so this was 7 nodes. If you had 8 nodes, then you would get something like this. So it's not perfectly balanced, because what you now have, the height of this is a 0. These are all zeros. The height here is 1. The height of this is 2. This is 1. And the height here is 3. So the heights are different. But they're only different by 1. So if you had another node here, then this isn't really balanced well. You would say, no, what you should do is move that over there. And that way, again, at least the heights would stay the same. Right? So if you think about it, there's something about the heights that tell you whether it's perfectly balanced or not. And you ideally want nodes at a level to have the same height. That is what perfectly balanced is. And we see there's a chance of an off by 1, because you're, like, if you had 8 nodes, you cannot pack it into 3 levels, right? So simply it's a binary tree. The only perfectly balanced ones are powers of 2 minus 1. That's the number of nodes, right? So if you have 1 node, 3 nodes, 7 nodes, or 15 nodes, you can get it to be perfectly balanced. Otherwise, you have this one imperfection by 1. Does this make sense, what I'm saying? Yes? Okay. So what the AVL trees do is they maintain this condition everywhere. Okay, so let me first give you a few definitions, and then I'll tell you what the AVL property is. So for a node x, okay, this is a definition. So I'm going to define a particular quantity. For node x, the balance factor at x is defined to be the height of the right subtree of x minus the height of the left subtree of x. Okay? So this is a quantity that I'm defining at all nodes. So just like I define the height of a node, now I define the balance factor of a node, which is, it's the difference between the height of the left and the height of the right. Now, if your tree was perfectly balanced, meaning that it was this tree here, what are all the balance factors? Yeah? 0. The balance factors are 0 everywhere because the left subtree and the right subtree have exactly the same height. But for this tree, this one specifically here, what is the balance factor of this tree? Yeah? 1. Why is it 1? Left subtree of this node, or the root. Doesn't matter, right? So there's some node. So this node has a balance factor of, in this case, -1. This node has a balance factor of -1. But this node has a balance factor of 0. And this node has a balance factor of 0. The leaves always have a balance factor of 0. Is this definition making, yes? Okay, so I'm just going to redraw this tree here. So I'm just going to write out the heights of all of the nodes, right? So the leaves are 0. The height of this node is 1. The height of this node is 1. The height of this node is 2. And the height of this node is 3. So let's look at the balance factor of this node. We're going to take the difference of the height of the right subtree and the height of the left subtree. So the right subtree has a height of 0. And the left subtree has a height of 1. So it's -1. Similarly, the balance factor at the root is also -1. Balance factor here is 0. Does that make sense? Right? So it's, if you think about it, so this is something that you'll have to code up, is it's almost like as I draw this picture, it should be fairly obvious. You can write a piece of code that, given a tree, computes the heights everywhere and then computes the balance factors everywhere. Right? If you know the heights everywhere, you can just look at the heights at your children and then you can compute the balance factor. And what we said is that the ideal value of a balance factor is 0. But for, if you have, in this case, 9 nodes, you cannot get a balance factor of 0 everywhere. No matter how you rearrange the tree, you get a balance factor of 1 or -1. Does that make sense? Yes? No, you're going to store it as part of the node. So yeah, so eventually when you implement these, you will store heights in the node. That way, whenever you do any change, you update the heights. But it's really a pain to do it when there's a rotation. That's why coding up AVL trees is a pain. Okay, so far so good. So everyone follows this? Okay, so what is an AVL tree? The AVL tree maintains the following invariant. Right? So remember, we talked about heap invariance, binary search tree invariance, and now we have what is called the AVL invariant. So this is also called the AVL property. And the AVL property, it's quite simple to state. It just says for all x, the balance factor at x is either -1, 0, or +1, which is like sort of the ideal that you could hope for. So for all nodes, the balance factor is -1, 0, or plus. That's what an AVL tree is. So this is an AVL tree. But this tree is not an AVL tree. This tree is an AVL tree. Does that make sense? Yes?
This is a generous definition, right? Because it allows for 3 levels.
Well, it's -1. Or the balance factor in any tree, even if you achieve perfect balance, right, you'll have a balance factor of either -1 or +1.
Okay, you can't just reduce it to just 0 and 1. There's no fault.
just there being 1. I guess you could, yeah, okay, you could probably have it, you mean just being 0 or 1. You could do that, yes. Yeah, you're right, you could do that. But if you think in terms of absolute values, this is the best. Okay? So that's what an AVL tree is. So what we're going to do is simply try to maintain this property after every insert or delete. Right? And that's where we have to do rotations and come up with the right way of rebalancing. Yes. But the first question you can ask is, okay, so how do I know that this tree is going to be balanced enough? Does that make sense? Like, so this is not entirely obvious, and so a theorem is an AVL tree of height h. This is being measured from the root. So an AVL tree where the root has height h has at least, so let me make sure I'm doing this. F of h minus 1 nodes where fk is the kth Fibonacci number. Yeah, you wouldn't think that Fibonacci numbers would appear here, but they appear quite now. So just let me remind you what the Fibonacci numbers are. So f of 0 is 0, f of 1 is 1, and f of 2 is 1. This is usually how we set it, and we'll just say that f of minus anything is also 0, just to have a sequence. And so now what we do is the next term of the Fibonacci is just the sum of the previous two, right? So f of 3 is going to be 2, f of 4 is going to be 3, f of 5 is going to be 5, f of 6 is 8, so on and so forth. Does this make sense? So this is some sequence, right? So there's a theorem that says, and I can prove the theorem to you. Maybe I'll do it at the end. I won't do it right now. But it's not very hard to prove by induction. So an AVL tree of height h has at least f of h minus 1 nodes, where h is the hth Fibonacci number. F of h. Maybe I should have said. Okay, I just put k just to say that k is generic. I want you to distinguish k from h. H is the height. Does this make sense? You're all a little puzzled. I mean, okay, you should be somewhat puzzled. Like, why is this even relevant? What am I trying to do? I'm trying to argue, okay, I want to show that an AVL tree with n nodes has a height of log n. And that's what I want to argue, right? Instead, what I'm going to argue is something sort of the opposite. Well, not really the opposite, something equivalent. I'll say that if a AVL tree has height h, then it has exponentially many nodes in h. Yeah. Okay, good. So let's just look at perfectly balanced trees, right? So I'm just writing the number of nodes here and the height of the root. So if the number of nodes is n, then the height of the root is like log base 2n, or like log n, right? That's what a perfect, I mean up to plus minus 1. But that's basically what you have in a perfectly balanced tree. So the way to think of this is that you fix the number of nodes and you bound what the height is. You say, look, if there are n nodes and the height is log n. But I can also ask the opposite question. If you have a perfectly balanced tree where the height is h, how many nodes are there? I can write this equivalently, yeah? 2 to the h, right? So if this is h, then this is like 2 to the h. Right? Because Because the exponential function is the inverse of the logarithm function. Yes? No? No. What do you guys do in high school math? I'd like it. Puzzles me, yeah. Right.
Okay, so question.
Yes, good.
We can figure out almost exactly how many nodes there are. Why are we lowballing this with Fibonacci sequence?
We don't know. We're trying to figure out how many nodes there are. This is perfectly balanced. But the AVL tree is not perfectly balanced because the balance factors are -1 or +1. And this could be cascading throughout. The root could have -1, +1, and then one of its children has -1. So it could be kind of leaning on one side.
So
It's at least Fibonacci.
maybe more.
Maybe more. But I'll show you that this is good enough. I'll show you that this is good enough. Because in the end, what do we all care about? We just want to bound the running time. Like that, we just want to say it's O of log n. But instead of trying to understand, given the number of nodes, what the height is, I'm going to go the other way around. I'm going to say, given the height, can I say that it has many nodes? So there are two ways of looking at this. One is to say, if there are n nodes, the height is at most blah. The alternate is to say, if the height is h, then the number of nodes is at least blah. No? Yes? So this is like saying, I want to say the height is at most log n. And here I want to say this is at least that. What you want to argue is as the tree becomes higher, it needs to have many more nodes to become higher. That's what this is saying, right? That's kind of what this is saying. That's why there's an at least over here. Make sense? Yes? No? So, and as someone pointed out, right, the exponential function and the logarithmic function are inverses of each other. So to go from the nodes to the height, you take the log. To go from the height to the nodes, you take the exponential. This is in a perfectly balanced tree. This is in a perfectly balanced tree. Not an AVL tree. But we'd like to argue something similar holds for an AVL tree. Although this isn't going to hold exactly because an AVL tree is not going to be perfectly balanced because it has a balance factor of -1 or +1. So it could be leaning in various ways. Does that make sense? But AVL or Adelson-Velskii and Landis showed is that you can bound it by the Fibonacci number. You say, why should I care about the Fibonacci numbers here? So the point is the Fibonacci numbers increase exponentially. Okay, so for example, if you were to plot the Fibonacci numbers, so this is h. I'm plotting what f of h looks like. It's going to look something like that. It's not, now your ideal is the function 2 to the h. That would be perfectly balanced. This is going to be a little below that, but it's still going to be exponential. So again, one has to prove this, but you can show that f of h is, roughly speaking, phi of h, where this is something called the golden ratio. So the golden ratio is, it's 1 plus root 5 divided by 2. It's like 1.6 something. The point is that instead of the tree growing as 2 to the h, it grows as 1.6 to the h. Does that make sense? That's what this theorem shows. So let me state this. Okay, so I'll just say this as a corollary, somewhat informal. An AVL tree with height h has at least 1.6 to the power h nodes. Maybe like -1 or something, but okay, this isn't precise. There's a certain error here, but ignore that. So roughly speaking, an AVL tree with height h has at least 1.6 to the h nodes. Okay? Now here's your question. So if an AVL tree has n nodes, what is the height? can you bound the height? It's the log base 1.6, exactly, right? So this means an AVL tree with n nodes has a height at most log base 1.6 of n. Right? So we know that this by a base change is it's log 2n, which is binary log 2 1.6. But this is just some constant. Right? So again, this is basically O of log n. I feel a lot of puzzlement and bewilderment. Either that or just boredom. Sometimes it's hard to distinguish the two. But so this is a good point to ask questions if you're confused. Yes?
Confused on the
At most. Yeah, this part?
Yeah.
Okay. So this is an at least here. So we say the number of nodes is at least 1.6 to the height. Right? So take a log base 1.6 on both sides. You get log base 1.6 of the number of nodes is at most the height. So I've just flipped that around, said height is at most that. Does that make sense? I've just taken logs on both sides. Maybe I should have done that. Maybe that makes it clearer. Yes?
So what operation is O log n that we're measuring here?
Sorry, say it again.
What operation is O log n?
Right now I've only bounded the height.
Okay.
But once I bound the height, then all operations are at most the height. Again, when you see O and omega, this is just talking about a function. It doesn't always talk about running time. Right? In this case, it's talking about the height of this tree. And the height of the tree is O log n. And once the height of the tree is O log n, then all operations are O log n. Insert, delete, and find. Does that make sense? Yes?
Where did the 1.6 come
1.6 comes from the bound that the Fibonacci number is exponential in the golden ratio. So this you have to prove. We could also prove this, but towards the end of class. It's not very hard to show this as well. But this is like a classic result known, and this is somehow where this magic, the golden ratio pops up over here. Yes?
Would you significantly change if we like expand the set of valid numbers, like include -2 and 2, like upper,
This one?
yeah, that one. Or if we remove it to just like 0 and 1.
It's a good question. I think that if you were to make it to -2 or 2, you would still get something exponential. But you would be dealing with a different sequence, where you could look at a sequence where you potentially add up not the previous 2, but maybe the thing that is distance 3 away and 4 away or something like that. But the same inductive proof should go through, and it will increase exponentially. Yes?
So does that just mean that as long as our balance factor is not growing, you can always get beta log n?
It's a good question. Yes, that's right. As long as the balance factor is a constant that's independent of the thing, I think you should be able to prove that. Although I think you can prove that. Yeah. You would basically prove that by induction, except you wouldn't get the Fibonacci sequence. You'd get some other sequence, you'll get the same bound, except you won't get 1.6. You'll get something worse than 1.6. Yeah, so the more balance factors you have, the worse this is going to become. Yeah. But it is surprising that you can just maintain this, which is the optimum. Of course, we haven't shown how to maintain the property, which is the hard part. But what we're saying is as long as the balance factors are going to be -1 or 1, the height is going to be log n. by the way, I'm not going to ask any of this in a test or anything. This is just so that you know. But this is where, like, what is very curious is in studying these data structures that seemingly have nothing to do with, logs and golden ratios and whatever, like all this stuff starts emerging here. It's like this sort of magical thing about math where, we're studying things that seemingly have no connection to like E or pi or something, and then E or pi will pop up. So sometimes these constants will just magically appear, and so the golden ratio appears in the analysis of the AVL tree. If much of this was confusing, there's just two things you need to remember. In an AVL tree, the balance factor is -1, 0, or +1, and this implies that an AVL tree with n nodes has a height of O log n. Right? We basically went from here to here doing like a bunch of math, but the math is not that, as far as the implementation is concerned, it doesn't matter. And most people who deal with AVL trees don't go around looking at the Fibonacci numbers. This is only for the analysis. Does that make sense? Yes? No? Right? And again, like, so maybe going into the math a little bit, the log function is the inverse of the exponential. So you can either talk of it as the height being logarithmic in the number of nodes, or the number of nodes being exponential in the height. And you can show either one of them and they imply the other. No. It's like dead silence, and then some people with their head like this, and yeah, and a few people asleep. I can see. I don't wake you up. It's fine. I assume even if you're hearing in your sleep, there's something at least you get. I wouldn't want to send you out because you're sleeping here. But, okay. All right, so we can come back to this later on. But do you all know what the balance factor means? Yes, balance factor. And does this statement make sense? I said it makes sense. It doesn't mean you know how to get there, as long as it makes sense. As long as it doesn't look like absolute gibberish, you're fine. And this 1.6, fine. It's something that emerges from somewhere. It doesn't matter. It's O log n. So the height is O log n in an AVL tree. So after all this analysis, what remains is to figure out how do you maintain the balance factor. Okay? All right. So we'll take a deep breath. We'll get away from math and go back to trees. So hopefully everyone is more comfortable. Okay? Okay. So how to maintain the AVL property, the AVL invariant. And I think this is where, frankly, when it comes to either implementing or teaching the AVL tree, it's much better than the other trees, because it's actually a much more transparent process here. Yeah?
Will we go over red-black trees or anything like that?
No.
Is AVL tree still a binary search tree?
It is still a binary search tree, right? So it's just a binary search tree that maintains this property, right? So red-black trees are another kind of binary search tree which have a different invariant. But the invariant is much more complicated to explain. It has colors, and you have to talk about like the red height and black children and whatever. It's a mess. It's a fairly ugly data structure, whereas the AVL tree is much more transparent. At least this is what I gathered from teaching it. Yeah.
What can you do with red-black trees that you can't do with AVL?
They're the same basically.
So why would anyone use a red-black tree? I thought you could like start one thing with a
Why? I think that like at that point then the constant factors matter, right? So then you could profile the various trees and see which is better. So although recently maybe a couple years ago I saw a paper that says that an AVL tree is about as good as a red-black tree. I think somehow red-black trees just entered the lexicon. People started using them and they became popular. Sorry?
color printers came out. People wanted to use the color.
Well, yes. And I think that's initially how they chose the colors, right? With those are the colors that they had in their printer, and they wanted to sort of mark the nodes. So, okay. So the AVL tree, the nice thing is, how do you insert or delete? Well, you just insert, delete like a standard binary search tree, right? You just insert and delete as normal. So now I'm going to ask you a question. When we insert or delete a node in a tree, in a BST, with height h and n nodes, for how many nodes does the height change? This makes sense. So I have some binary search tree. I went ahead and I inserted. For how many nodes does the height change? Theta of 1, theta of h, theta of log n. Okay, so how many, let's just say worst case. Actually, no, did I get this correct? For how many nodes is the height going to change? So the height is h. For how many nodes is it going to change? The tree. The tree. No, no. You insert one node. You insert one node, some heights are going to change. Does that make sense? You insert, so here's a binary search tree. You went ahead and you inserted something. So you're going to add this. For how many nodes does the height change? Any BST. Any BST. Take any BST, make an insert for how many nodes is the height going to change. And if you want, look at some BSTs here. There's a BST. And you go ahead and insert. For how many nodes does the height change? What is the answer? Yeah, it's h, right? I mean, you don't know that h is log n, so you're not sure. So it's h. Basically, in the worst case, okay, so which are the nodes where the height changes, yeah? And the parents of those, and the parents of those? The ancestors. So when you insert a node, or you delete a node, it's only in the ancestors that there's a change in height. All the other nodes stay the same, right? So if you, for example, insert here, then the height changes potentially on all of these, but it's never going to change anywhere else. And the same thing, if you delete this node, then the height changes over here. But the heights don't change anywhere else. This is really important. So when you implement your AVL tree, you'll do an insert or delete, you have to update the heights. But you don't have to update the heights everywhere. You only have to update it on the ancestors. And if the height is log n, then that's only log n times. So when a node is inserted or deleted, heights change only on the ancestors of, well, I'll say a node X is inserted, ancestors of X. Right? So it's the same for an insert or a delete. So in an AVL tree, the height is O of log n. So the total height, so height of the root. So the heights change only at O of log n nodes. Again, I'm drawing this picture again. If you insert somewhere here, then you look at the path all the way to the root, and over here, the heights may have changed. They may have changed, they may not. Like, there are situations where the height does not change. For example, if you have something, suppose this node already had another leaf. By inserting this node over here, you don't change any of the heights, because the height of this node already was 1, and so on and so forth. So the heights may change, they may not change, but you know that for all the nodes outside of this path, the heights cannot change. Like if you have some node here, it doesn't have a path that goes to this inserted node, or at least a path down to the leaf. Like it doesn't have a downward path that goes to this, so it cannot change its height. Yes? Well, okay, so that means, well, let me say something and then I'll answer your question, right? So the heights only change at these nodes, and the balance factor only changes at these O of log n, which is an O of h nodes. Okay? So the balance factor is only going to change on these nodes, because that's the only place that the heights are changing. And remember, the balance factor was the difference between the height of the left subtree, the right subtree, and the left subtree. And the balance factor only changes if the height of the left or the right changes, right? So it's all about looking at the ancestors of the inserted or deleted node. Does that make sense? Those are the only places where the heights actually change. And does that answer your question? Okay. Does that make sense? So the balance factor is only changed on these nodes. So why are we doing this process? Well, we're going to insert like a normal binary search tree. Then we have to find out where the balance factors got affected, rotate it back so that it's back to -1, +1, or 0. And the only nodes where you have to do that are these. So that way you don't have to look at the entire tree to rebalance. Yes?
So what happens if the branch that you end up going down to insert or delete a node ends up being, I guess you could say, shallower than the opposite side of the branch?
Okay.
Would you just not change the height?
So well, you have to recompute the height on these nodes. Does that make sense? No, I haven't answered your question. So,
Like, for example, in this drawing that you have here, if we were to delete the node that you put an X on,
that one.
would we want to change the root node's height even though there's something deeper?
No, then the height will not change, right? I mean, the height is a fixed quantity. The height is a defined quantity. The height might get updated, it might not. So you have to go and do an update. So you'll have a piece of code that updates the height.
So would we need to have some way to check?
You have to have some way to check, did the height change or not?
And would we do that by comparing their children's heights?
Exactly. So there is a simple formula, right? The height of a node is the maximum height of the left and the right plus 1. So you apply that formula. We'll talk about that in a bit, right? So for now, let's just I'll talk a little bit more about how you would code these things up. But for now, just understand this at this level of, okay, the heights are going to change here. So the balance factors are going to change only at these log n nodes. Because we're assuming the depth is log n. The height, whatever, the height, depth, they're all log n, right? Because we know it's an AVL tree. So things were log n to start off with. We're going to insert or delete. So what we do is we insert or delete like a standard BST. Then we find all nodes where the balance factor is not in -1, 0, or 1. And for all these nodes, we need to fix the problem. And so we can end right here the lecture, right? That's it. We fix the problem. Then you're done. You have an AVL tree. Okay? Right. So does this make sense? To find all the nodes where the balance factor is not in -1, 0, or +1, you only have to look at the ancestors of the node that changed, which is the insert or the delete. Yes?
Why don't you just fix the first one you find
When you walk down?
when you walk up?
Yeah. So essentially that's the way you do it. They're kind of like, yeah, they're kind of together. Right, exactly. But just conceptually, I just want to split these apart. But when you implement it, you'll sort of do these together. Every time you find a node, you'll fix it. But we'll see that it makes sense to fix it bottom up. That's the way that we're going to fix the problem. Okay, does this make sense so far? Okay, now we're actually going to talk about the fixing, which is more complicated. Right, this is where we have to start doing rotations to figure out how to do it. Before we get there, ask you a question. After a single insert, by how much can the balance factor change at a node? I mean, I'm asking, what is the worst case? The maximum possible. Right? So after you do an insert, the heights change, so the balance factors change. And I'm asking, by how much can it change? This question makes sense? By how much can it change? Is it going to change by just a constant? Could it change by like log n? Or could it actually change by n? So I'll give you a few minutes to think about this. All right, so what is the answer? How much can it change by? That's right, it can only change by theta of 1. Even more specifically, it changes by at most 1. right? Because when you insert a node, any height can change by at most 1. Even when you delete, it can only decrease by 1. And you're only looking at the differences of heights, so the change is at most 1. So your problem is that a balance factor becomes either +2 or -2. And then you have to fix it. Okay? So that's so the balance factors changes by at most 1 or -1, right? I mean, we fix the problem bottom up, meaning we're going to find all the nodes where the balance factor is not in -1, 1, and indeed they'll be on this path. So we'll keep going up. We'll check, is the balance factor out of range? And if it is, we fix it. And then we fix it, then we move up, and fix it, move up, so on and so forth. Okay? And so suppose the balance factor at a node x is -2 or 2. We need to fix it. We can assume the balance factor at all descendants of x is in -1, 0, or 1. Okay, let me repeat the statement. Suppose the balance factor at a node is -2 or 2. We need to fix it. We can assume that the balance factor at all the descendants of this node x are correct. Why? Yeah? Exactly, because you're doing it bottom up, right? So you've fixed all the problems below. So in this example, suppose there is a problem at this node. We're fixing it bottom up. So we're fixing the problem at everything up to that path, and then we fix it over there, which means that for the descendants, the balance factor is correct. Okay? So you need to be really awake for the rotation, so I'm going to take a break for a few minutes. Okay, so let's take a break for a few minutes, and when you come back, I'll show you how to rotate and fix the AVL tree. Okay, let's let's continue with rebalancing the AVL tree. Okay. So the balance factor at a node is either 2 or minus 2. We need to fix it. So let's recall again, the balance factor at x is the height of the right child of x minus the height of the left child of x. And so this is either 2 or minus 2. That's the problem case. So in your code, you'll have, like, if it's 2, do something. If it's minus 2, do something. These are basically just mirrors of each other. Like, there's a lot of replacing left with right and things like that. So I'm not going to do both the cases. I'll just do one of them. The other one is analogous. So I'm going to assume that it is 2 and show you how to fix it. And then you just have to sort of mirror the entire picture for the case when it's minus 2. So just to say this again, so what this means is at x, the height of the right child minus the height of the left child is equal to 2. Right? This is the situation that we have. So, and I'll just do that. Right? So the height of the right child is equal to the height of the left minus 2. But for all strict descendants, there's no problem. So let me draw case 1. So here's x. Here are the two children of x. And so I'm just drawing, okay, so well, put it this way. So let's just say that the height of the left is h. So we know that the height on the right is h plus 2. Right? So the height here at this node y is h plus 2. Now this height of h plus 2 could be coming either from its left or right. That makes sense? So it's like saying that anytime you have a height, it's because there's some leaf that's at that distance. So there's some leaf that's at a distance of h plus 2 from y. That leaf might be at the left or the right, and that's going to give us case 1 and case 2. So let me just draw this picture here. So I have D3. Sorry, the best way that okay, so let me just draw this picture and then we'll talk about it. It's like a bunch of Christmas trees, I guess. But okay, so what I'm saying is in this case, so we know that the height of the right child is equal to the height of the left child minus 2. The height of the right child is h. The height of the left child is h. The height of the right child is h plus 2. Now this h plus 2 can either come from the left or the right. So what's the picture that I'm drawing is that this has a height of h plus 1. This node over here could have a height of either h or h plus 1. This node has a height of h or h plus 1. So if you think about it, it has the same height as T3 or it has 1 less. It cannot have anything even less than that. It cannot be less than h. The height of T2 cannot be less than h. Why? Why? Yes? No, there's a more specific reason as to why is it. Okay, does this picture so far make sense? Right? The height of T1 is h. The height of y is h plus 2. Now, y has a height of h plus 2 because somewhere one of its children has a height of h plus 1. I'm assuming that it's the right one. Yes? No, I'm assuming, so why can't the height of T2 be h minus 1? No, but T3 could still be h plus 1, and T2 height would be h minus 1. And the max of those two is h plus 1, right? Because the height is, or yes? Almost. Yes. Okay. It could be 2. If this was h minus 1, the difference would be 2.
We're solving from the bottom up, so we're assuming everything below it.
Exactly. Give him a round of applause. We're doing it bottom up, right? We're assuming that the balance factor are all strict descendants, I should say. So we fixed the problem everywhere else. So this can only have a height of either h or h plus 1. Does this make sense now? Because we're doing it bottom up. So we know that the problem is here and in ancestors, but not in descendants. So what we're going to do is we're going to fix this by a rotation. So what you want to do is T3 has to move up, and T1 can move down. So if we rotate this way, we'll fix the problem. Okay, so we rotate this way to fix the problem. So y will move up there. X is going to move down. Then X is going to have a child T1. T2 is going to switch. And okay, so let me make sure I'm drawing this correct. Yes. I mean, the trees, of course, I've messed up the sizes. But note what happens here is this height, right, is h. This height is h plus 1. And so this stays at h plus 1. And this height, it's either h or h plus 1. It's h or h plus 1. Does this make sense? So what has happened is that this part moved down and this part moved up. And so now the balance factors are correct. And so the problem has been fixed. So when you do a single rotation, you can fix this. What is case 1? T3 is the highest. That is the situation. So when T3 is the highest, this rotation will fix the problem. Remember, we're assuming that the balance factor is 2 to start off with. So at x, it's h and h plus 2. But this h plus 2 is coming from the h plus 1, which is T3. And we know that we fixed the problem at h2 if there was a problem. We're assuming that this is the highest. So T2 is either h or h plus 1. And this rotation will fix the problem. Does this make sense? So this is really where, when you write code for AVL trees, things go wrong, is because when you start doing all these changes, you forget to update a height or a balance factor. And when you make those mistakes, then it's pretty hard to debug. Right? But that's where you have to sort of do it really carefully on small examples. Okay, but does this make sense? So then you fix the problem when T3 is the highest. So there's another case, which is case 2, which is T2 is the highest and T3 is not the highest. I mean, the reason I say this, I mean, these are sort of equivalent, but if T3 was the highest, you could have done this. You could have done case 1. So you now have to deal with the case where T3 is not the highest. And so let me draw a picture over here. So you have X. So remember T1. This height is H, right? So this is H. We're looking at Y. The situation that we have is, now, so this has a height of H. This needs to have a height of H plus 2. And that's coming because T2, this has a height of H plus 1. So the difference between this is like 2. Right? That's sort of the gap. And what's happening here, now remember, there is no problem at Y. And hence, T3 has a height of H. If T3 had a height of H plus 1, we could apply this situation. Because this is, if T2 is H or H plus 1, and T3 is H plus 1, we can do case 1. So we are in case 2, where T3 is not the highest, right? It's smaller. Okay, does this make sense? So in this case, this is the complicated case where you have to do what's called a double rotation. You have to do 2 rotates and you fix the problem. So I'm going to, does this picture make sense so far? Any questions? Right, you see the difference between this picture and this picture, right? Okay, so now in this picture, what we actually have to do is we have to move this over there and then this over there. So let me open it up a bit. Let me draw this picture again. So X, T1, right, so this has height H. There is Y here. T3 with a height H. And this has height H plus 1. And so now it could actually be on either, like, okay, so this is a bit, I'm going to write this as T2 and T2 prime. So there are 2 trees here. One of these is deeper. Like it could be either T2 or it could be either T2 or T2 prime. But one of these is sort of deeper than T3, right? It's higher. So the way we fix it is we move that there and then we move that there. You know, you have to go draw the pictures and make sure that what all of this is correct. So the first rotation, is X, Z moves there, Y moves there, T3, and Y gets T2 prime. Z is going to get T2, and then T1. So what happens is actually, this doesn't fix the problem in certain cases, but then what you do is, once you rotate that over there, it will fix the problem. Now, I'm not going to sort of work out all the heights right now, because it's just a matter of sitting down and writing them all down. What I will do instead, which I think has more value, is to basically show you a visualization that does all of this. And if you just experiment with it, you will see all of these. But this is the picture that you need, right? In case 1, you do 1 rotate. Y goes to X. In case 2, there's a double rotation. You first do this rotation, and then you move z up. Z goes to y, t3, t2 prime, x, t1, t2. So that's sort of that's the change that happens. Z is going to move there and then there, and the way you end up is that z ends up with the children x and y, and if you check all the heights, it will be correct. Yes?
I might have misheard, but I think I heard you say that, like, after the first rotation, there may still be a problem. So are there cases where you only need to do the first rotation and don't have to do the second?
It's a good question. So I think that if I am not mistaken, no, I think you always have to do it. I'm sorry. I think you always have to do it. Because what happens in this case is it could be that T2 is going to go up and T3 is going to come down. And so I think, so I think you always have, because T3 is going to come down, T3 is going to end up with a height of h plus 1. And so you'll still end up with a height of h plus 2 at that point. And so you have to do the second rotation. You always have to do both. Yeah. Yes? How I'm getting z? You mean what is z? Z is the left child of y. So the idea is that in this case, you don't have to look at z because your problem is, okay, so in some sense what's going on is, in this case, we're assuming the problem is at the right child. But then that problem is coming from either the right child or the left child of the right child. So one of the grandchildren. Right? So the thing is, there's a problem on the right side. That means that the right side is too high. But if the right side is too high, look at the right side. Now, its left or right is too high. Right? So if you look at from x, the problem is either T3 is too tall or T2 is too tall. If T3 is too tall, then there's one rotation that fixes it. If T2 is too tall, that's this situation, you actually have to look at the root of T2 and do a double rotation. Yeah, kind of, sort of. At this point, let's use some technology beyond pen and paper. Sorry, it's on that side, not this side. So my apologies to those who are sitting here. Actually, no, wait, I can do both, of course. Yeah, there. Technology. Okay, so I have shared this visualization with you, so you can play around with it yourself. Okay, so this is an AVL tree visualization. Can everyone see? Yeah, okay, so insert, so it inserts there. That number at the top is the height. Annoyingly, this measures height with the number of nodes, not the number of edges, so there's an off by 1, but I changed it to edges because I wanted leaves to have a height of 0. But it doesn't matter. Okay, so this is just doing an insert. It's just going to insert as a binary search tree, and note that it updated the heights. So the heights are, again, measured with nodes, not edges. So the height here is 1. The leaves have a height of 1, and then so on and so forth. Okay, so let me insert. Okay, so pay attention here. So what's going to happen is when you insert 30, 30 is going to be the right child of 20, right? So it's not going to be an AVL tree anymore, and then it's going to do a rotation to fix it. So okay, so it's going to go there, and it's going to insert. So it's updating the heights, so 2 and 3, and then it's going to do a rotate to fix it. So I'm warning you, so 30 is going to go in. The thing is, if I can pause it, but then I have to like skip back and forth. It's a bit, okay, maybe I can, let me see. Right, so the heights are being changed here. Okay, so at this point, you can see the heights 1, 2, and 3. Right? And so there is a problem now at 10. Right? So we're exactly in this situation here. So let me see if I can, sorry. We're exactly going to go in this situation where T3 is going to be the highest, because T3 in this case is 30. Right? See that there is, so the balance factor at this node is going to become 2 because its right side is 0, and the right has a height of 2 and the left has a height of 0. Right? And in that node of 20, which doesn't have a problem, but still its tallest is to the right. So it's exactly case 1, and a single rotation. Y is going to rotate to x. So the y in this case is 20. Okay? It's going to rotate. And so that it does that rotation. Let's do a few more, and then you'll see. So let me insert 40. So it's going to insert 40. At this stage, there is no problem with the heights. Right? The balance factor is still accurate. Yes? I am inserting only at the right side. You can insert at the left and right, and we'll see. So that's what I was going to do next, actually. So now let me insert 35. Okay, so insert 35. Okay, so I'm pausing here because what this is doing is actually not even updating all the heights. It's fixing the problem right there. There is a problem at 30 because its left has a height of 0 and the right has a height of 2. But the right side, its tallest child is to the left. So that's exactly this case here. T2 is the highest and T3 is not the highest. It's this situation. It looks like this. So x is 30, y is 40, and the T2 is 35. So it's going to do a double rotation, and the problem with this animation is it does it all in one go. But the idea is that what's going to happen is that the 35 is going to end up at the root, right? Because what happened in that double rotation was that z moved that way, right? So z ends up with children x and y, where z was this grandchild. So 35 is going to end up with the children 30 and 40. Okay, so it does that. It does it. And so if, let's say, we insert 50. So I'm just doing it all on the right side just so that the pictures look the same. So there's going to be no problem here now. Or no, wait, there is going to be a problem. Okay. So there is a problem now at the root because the height is